Good afternoon, everyone. So let's take a look at number 20, Problempalooza with standing waves. For this, you guys were asked to figure out how the wavelength measured on different standing waves. And since it's been a while, I figured I'd make a video key to help you out. So remember, one transverse wave is one complete pattern of up and down. So that means every two complete antinodes equals one wavelength. So drawing these on here, it says draw a line representing a wavelength. So that'd be drawing two complete antinodes. So this would be my one wavelength from here to here. Two complete antinodes, one wavelength would be from here to here. And one wavelength would be this section right here. Two complete antinodes equals one wave. Because remember, it's one complete up and down, but it doesn't include this reflected wave. So, to calculate the wavelength then, I used the wavelength equation, the 2 pi L over N. For A, I used L of 25 centimeters, and N was equal to 1, 2, 3, 4, 5. This is the N equals 5 harmonic because there's 5 antinodes. Similarly, this is the N equals 7 harmonic because 7 complete antinodes. Someone asked me the other day, they were like, well, I see that D has 1, 2, 3, 4 nodes. Does N equal the number of nodes? I mean, that would make sense, right? N nodes. But the answer is no. It's the number in the pattern. So this would be the 1, 2, 3. This is the third harmonic. And as a result, when I rank the wavelengths of this wave from greatest to least, I see that both C and D have wavelengths of 20. A has a wavelength of 10, and B has a wavelength of 8. I should probably write a B there. The wave speed from greatest to least is all the same because remember, even though you can use these equations, V equals D over T and V equals lambda F, in order to calculate speed, those are not what speed depends on. For a wave on a string, the speed is related to tension. So since they all have the same tension, they all have the same medium, so they are all the same wave speed. And that means when I go rank frequency from greatest to least, I can actually use this wave equation here. Remember, what this equation says is the velocity stays the same, and as a result, if wavelength decreases, then frequency increases. Those two are an inverse relation. And since they're inversely related, whichever one has the smallest wavelength has the largest frequency, yielding simply a reverse order from part B. If you want to try this out, one thing you can do is just pick a speed, like, I don't know, 10. If I picked a speed of 10 and then entered A's wavelength and C's wavelength and B's, etc., you could calculate out their frequencies and then rank them. So, for these patterns then, on each of my diagrams, I drew a standing wave that had an increasing number of harmonics. So 1 antinode, 2 antinodes, 3, 4. I tried to draw them all the same length, so representing the same string, so the same length. And it says to draw the wavelength on each diagram. I kind of ran into a problem here though. Don't know if you see it. But 4's wavelength, I got that. That's the length of 2 antinodes, one complete up and down. 3's wavelength, that's the length of 2 antinodes, one complete up and one complete down. I don't know if you see where I'm getting this problem here. 2's wavelength is this big, one complete up and one complete down. Ooh, man. Do you notice the problem? The wavelength is getting smaller and smaller, larger and larger. As I go up, the wavelength is getting larger. Before it was this big. Now it's this big, now it's this big. In order to get 2 complete antinodes, this one, put a little star next to it, my first harmonic, my wavelength is larger than the string. Okay, so that means as a result, when I do this out, this wave goes all 1 complete up and 1 complete down would be like over here. So what I'm going to do to draw that so I don't make my paper really messy, 1 wavelength, and I'm going to draw it as if it's going to continue all the way out here. Okay, that little arrow on the end means the wavelength is bigger than the string. Okay, pattern time. So, things you should remember from class, but it's okay if you don't. Wave speed is the same. This is all the same string, all the same speed. That is one pattern that we like. That's an easy one. All the same because it's all the same string, all the same tension, all the same wave speed. So 500 down the board. Okay? Another pattern we can use is let's use this wavelength pattern. This one says I can take 2 times the 0.6 length. Right here, this means L is equal to 0.6. And substitute in n equals 1, n equals 2, n equals 3, and n equals 4 to get these wavelengths. As you can see, the smaller the harmonics, the larger the wavelength. Then, choices, guys. I can either, well, let's see. Actually, you know what? I can't do this for this. But let's say that I, across any particular row, need to obey the wave equation. The wave equation says that across any particular row, wavelength times frequency is equal to wave speed. Dividing out 500 divided by 1.2 gives 416.6. We'll call that 0.7. Okay. So let's see pattern-wise. This pattern is that wavelength times frequency equals speed. So across any row, I can use this. And if I wanted to, that means I can use that pattern 3 more times to get my missing frequencies. But just so that we see all the patterns together, the last pattern then is that for harmonics, the higher the frequency, the larger number of harmonics. And it's all just simple multiples. So for instance, my 4th harmonic is just 4 times my 1st harmonic. And my 1st harmonic is so important. This is called my fundamental frequency. It's the main note that I hear when I listen to a sound, but it's also fundamental because it's important. If I multiply this by 2, I get my 833, I get my 2nd harmonic. If I multiply that same 416 times 3, I get 1,250. That's my 3rd harmonic. And times 4 gives me my 4th harmonic. So, pattern-wise, the string is all the same medium, all the same speed. Wavelength should decrease with number of harmonics, and frequency should increase, but as multiples. So if I wanted the 7th harmonic, it would be 7 times the fundamental, etc. And finally, across any row, wavelength times frequency has to equal wave speed. So, I messed up in part D here. I gave you a time that did not make sense. And the reason this time did not make sense is that that time represented 500 meters per second traveling 250 meters. But guys, that 500 meters per second is the guitar string. Unless I'm at like a really crazy concert where they literally pick up and throw the guitar string, the wave, the sound wave that travels to the end of the stadium travels at 340 meters per second. So I should have given you this. My bad. This is the speed of sound in air. Obviously goes faster and slower in different materials. So my wave sound travels 250 meters, and the 250 meters divided by 340 gives me a fraction of a second. Right? So 250 meters is the distance over 340 meters per second. Takes a fraction of a second for that sound to reach the other end of the stadium. So, then we have part E, the fundamental frequency. That is my F1 first frequency. So I know F equals 14.167 hertz. Now it's traveling through air. So that's a speed of 340 meters per second. So to get the wavelength, I use the wave equation. 340 is equal to lambda times 416.7, dividing those all out, and I should get some fraction of a meter. Yep, that's 0.816 meters. So what changes can we make to play a lower fundamental frequency? So the fundamental frequency is F1, this 416 number. And notice that it depended on both the wave speed, which depended on the string, and the wave length, which depended on the length of the string. So if I wanted to play a lower frequency, I could increase L. And you guys know this from playing the guitar or ukulele. A longer string means a lower note. Increasing L means a longer wavelength and therefore a lower frequency. I could put less tension on the string. Less tension lowers the wave speed. And you guys know this from guitar because this would be like you loosening the tension on the guitar string and it playing a lower note. And last guitar-related one. You could also use a thicker string. Don't know if you've noticed this before, but guitar strings all have different thicknesses. And your heaviest, most massive strings all have a lower wave speed and therefore a lower fundamental frequency. You could rearrange this to read that, well, speed is equal to wavelength times frequency. Ergo, frequency is speed over wavelength. So I could make a lower speed or a larger wavelength to change the frequency. Now, we come to the piccolo, and this problem is similar. I'm still going to be doing the 1, 2, 3, 4 harmonic. I'm still going to be drawing the same diagrams where it has antinodes and nodes alternating. So antinode, node, antinode, node, antinode. A wavelength will still be one complete up and down. So that's up, down, and back. So this wavelength is as long as the tube itself. So let's draw that out. This needs to have one complete antinode. So a node in the center, antinodes at the end. And remember, the antinodes occur at the end of an open tube instrument because that's where the air goes into the tube and out of the tube. This harmonic, just like with the string, has a wavelength that's longer because this is only from up to down. It needs to come back. This wavelength technically goes like all the way out here, but I'm just going to draw it as bigger than this diagram will allow me to draw. Wavelength is bigger than the tube. I noticed for 3 that for some reason this printed out smaller. My third harmonic needs to have 3 nodes, 1, 2, 3, in order to make 3 complete antinodes. So it'll look something like this. And if you get to the end and you're trying to check to see if you drew them right, keep in mind this would be 1, 2, 2.5, 3 complete antinodes, so that must be the third harmonic. And the wavelength for this one would be 1 complete up and down, so it would be this long. So notice again the pattern that wavelength is getting smaller as harmonic increases. Last one. So in this case, I've got my fourth harmonic, and I'm going to double check at the end that I drew this upright. Antinodes at the end. This is a half, 1.5, 2.5, 3.5, 4 complete harmonics. This must be my fourth harmonic. One wavelength is one complete up and down, so one wavelength. Now let's deal with math patterns here. This is all a tube filled with air, so all the speeds are identical. Oh, I like that pattern. All the same. Across every row, I can use V is equal to lambda F. I can use the wave equation. So dividing across, that's 340 divided by 251.6, gives me a wavelength of 1.35 meters for the first harmonic. So keep in mind, this is the wavelength greater than L. So the wavelength of this is 1.3 meters from here to here. L must be approximately half that. So we'll keep that in mind for later. Okay? So next, let's use the pattern for frequencies. We know that all the later harmonics are just multiples of the original, the fundamental. So 256.1 times 2 times 3 and times 4, that's 503. 1000.6 254, or sorry, 754.8, and then divide across each row to get wavelengths. So 340 divided by 503 gives me a wavelength of 0.6. We'll call it 0.68. 0.45, and I should see wavelengths getting smaller as frequencies get bigger because these are inversely related as the speed stays the same. Okay, so awesome. I see that my wavelengths should be getting smaller. These are all the same speed, and my frequencies should be increasing. Length of the piccolo. I know this is L over N is equal to wavelength. So pick any wavelength on here. I'm just gonna pick one to be easy. Let's say I pick the fundamental frequency, the fundamental wavelength. 1.35 is equal to 2L over 1. Therefore, I can solve for L. Is going to be 0.68 meters. Divide by 2 on both sides, L is equal to 0.68. Because the carbon dioxide is heavier and sinks to the bottom of the room, that means the speed of sound is smaller. Since the speed is less than 340 meters per second, that means the same frequency would play, the same tube, same wavelength, would play a lower note. Let me rephrase that in case that was unclear. Because the frequency you hear depends on the wave speed and wavelength, making a lower speed makes a lower frequency. And I know it's a lower speed because a heavy gas sinks to the bottom of the room, and the heavy gas has particles that are heavier and harder to move, so lower speed of sound. For the fast Fourier transform, that means I'm just drawing my peaks in. The 4 frequencies that were calculated for this tube were about 251, 503.2, 754, and about 1,000. So these are the first, second, third, and fourth harmonic. You get one peak for each of those harmonic frequencies. And don't worry about drawing the correct amplitude. A thing to be aware of is this fundamental frequency should be the largest amplitude, usually. So, depending on what your group did, you will either be doing this all electronically or all in person on Friday before we left for our online learning. For this, I'm going to put a key that only has the electronic values, but in either case, what each group was doing was measuring the length of the tube to calculate the wavelength and using the wavelength along with measured frequencies to calculate the wave speed. So check the key on this later. This will have data filled in for the groups that did this electronically. Best of luck.